All right, so at this point we know how to decompose our model into a stochastic and deterministic component, write the negative log likelihood function for that model, and find the maximum likelihood estimates for the parameters in our deterministic model by minimizing the negative log likelihood with R. As far as maximum likelihood estimation is concerned, that's it. We know how to obtain maximum likelihood estimates, at least for models where we can consider the data independently drawn from our distribution of choice. If all we want is estimates, we can stop here. But the maximum likelihood estimate is a function of a random variable, and therefore it is also a random variable, which means that it has a distribution. And it's frequently the case that to characterize more than just the mean, that we want to characterize rather, more than just the mean of that distribution, we're going to want to characterize at a minimum the dispersion around that mean, which is a reflection of the uncertainty in our estimate. That's what we'll be learning today in this part of the lecture. We're going to characterize uncertainty in the maximum likelihood estimate in two ways. We'll go over how to calculate the standard error of the maximum likelihood estimate and how to calculate confidence intervals for it. In the last part of this lecture, we plotted the Bernoulli likelihood function for various values of the parameter p and for various amounts of data. When we did this, one thing that I pointed out is the increasing curvature in the likelihood function as we acquire more data, and how, loosely, this reflects an increased certainty in the maximum likelihood estimate. Well, it turns out that we can use the curvature in the likelihood function around the maximum likelihood estimate to obtain a standard error for the estimate. The way we do this is by taking the second derivative of the log likelihood with respect to our parameter, which in the case of the Bernoulli and binomial distributions is p. Let's illustrate this a little bit. Here I've plotted the likelihood curves for the binomial distribution, where in the first plot, n equals 10 and x, our observed data, is 6. This makes the maximum likelihood estimate for p equal to 0.6. In the second plot, x equals 60 and n equals 100. So the maximum likelihood estimate for p is still 0.6. However, while the peaks are in the same place, it's clear that the curvature around the peaks is quite different. In the second plot, where n is 10 times higher than in the first plot, the peak is much, much steeper. Let's plot the log likelihood instead, and let's zoom in on the x-axis so that we're only looking for values of p between 0.55 and 0.65. In other words, we're just looking at a narrow window around the maximum likelihood estimate. These look pretty similar. Now let's take the derivative of the log likelihood function and plot it. The derivative, of course, gives us the slope of the likelihood function at any given value of the parameter. It tells us whether the log likelihood is increasing or decreasing at any given point. So of course, it's positive below the maximum likelihood estimate, negative above it, and 0 at the maximum likelihood estimate. But pay attention to the axes on these two plots. The slope of the log likelihood function is changing much more quickly across the maximum likelihood estimate in the second case where we have more data. Finally, let's plot the second derivative, which expresses the rate of change of the slope of the log likelihood at any given value of our parameter. Take a look at the value of the second derivative at the maximum likelihood estimate of 0.6. It's much, much more negative when n equals 100 than when n equals 10. When we evaluate the second derivative of a log likelihood at the maximum likelihood estimate, values that are more negative indicate a greater curvature around the maximum likelihood estimate. This, it turns out, is really useful thanks to this thing called Fisher information. The Fisher information, strictly speaking, is the negative expectation of the second derivative of the probability density of our random variable, uppercase x, given the true value of our parameter theta. And it can be shown that the variance in our maximal likelihood estimator is approximately the inverse of the Fisher information. Note that this value, the log of the probability density, given the true parameter theta, is almost the log likelihood, except that theta isn't known because theta is what we're trying to estimate. So in practice, what we use is something called the observed Fisher information, which is the negative of the second derivative of the log likelihood at the maximum likelihood estimate. If we're working with the negative log likelihood, this is just the second derivative at the maximum likelihood estimate. No minus sign required, of course. Then we take the inverse of this value to obtain the variance of the maximum likelihood estimate. But what about when we have multiple parameters? Like here where we have pictured the likelihood surface of these two parameters, theta 1 and theta 2. Well, this actually generalizes really nicely to any number of parameters. In the case where we have multiple parameters, instead of just one value for the second derivative, we have a matrix of second derivatives and second partial derivatives, which is known as the Hessian matrix. When we invert this matrix, it doesn't give us just one value for the variance, but instead a matrix of variances and covariances. In the case of our two parameters, theta 1 and theta 2, the variances of theta and theta 1 are on the diagonal of the matrix, and the covariance between theta 1 and theta 2 are off the diagonal. I know this might seem complex, but luckily R makes this really easy. Here again is our negative log likelihood function for the normal distribution, which we've already seen, and we've simulated 100 random values from a normal distribution with mean mu equals 4 and standard deviation sigma equals 2. The code to obtain the maximum likelihood estimates of mu and sigma is the same here as before, except now we've added an argument, Hessian equals true, indicating that we want Optum to return the Hessian matrix around the maximum likelihood estimate. Note that since we're working with the negative log likelihood, this is already the Fisher information, no extra steps required. So if we print the value of this variable MLE, which we've stored the output of Optum to, what we'll see is this Hessian matrix here, and that is the Fisher information. To obtain the variance covariance matrix, we just invert the Fisher information matrix with the solve function. And if we print that value, here's what we see, the variance covariance matrix. The variances are on the diagonal, and the standard error is the square root of the variance. So we obtain the standard error for each of our estimates by just taking the square root of the diagonal of our variance covariance matrix. And with just 2 extra lines of code, we have the standard errors of our parameters and their variance covariance matrix. Another method we might use to calculate standard errors is bootstrapping. Bootstrapping is a very simple and powerful concept, which at first might just seem like magic, but it works very well. Loosely, the idea with bootstrapping is that if our data are random and independent samples from the population, then we can resample with replacement from the data we already have to obtain another random sample. Note that for all the problems we've introduced so far, we've been assuming that our data are independent and of each other after taking into account our model. So we're actually not introducing any additional assumptions here. Here are the 3 steps we need to obtain bootstrap standard errors for our maximum likelihood estimate. If we have n observations, we sample n observations from the data with replacement, meaning that data points that we have already sampled can be sampled again. We do this many, many times. For each sample, we obtain maximum likelihood estimates for the model parameters. Finally, we take the standard deviation of those per sample maximum likelihood estimates. Since the standard error is the standard deviation of the distribution of an estimator, this value is our standard error. Bootstrapping tends to work best when we have lots of data points and when we take lots of bootstrap samples. The latter is just a matter of compute time. Thanks to modern processors, we can obtain hundreds of thousands of bootstrap samples for simpler models in basically the blink of an eye. Let's go through how to run a bootstrap in R from scratch. There are packages which make this a lot easier, but all of them are just going to be basically doing this under the hood. So as before, we simulate 100 random data points from a normal distribution with mean mu equals 4 and standard deviation sigma equals 2. Here's what these data look like when I ran this. Let's define a variable, n_obs, which is the number of observation, and another variable, n_samples, which is the number of bootstrap samples we'll take. Here I did 1,000, but you'll usually want to run a lot more. Next, let's initialize an empty matrix to store our bootstrap maximum likelihood estimates, which I'll call MLE_samples. Because we have 2 parameters, mu and sigma, the matrix will have 2 columns. And because we're taking 1,000 bootstrap samples, the matrix will have 1,000 rows. Here's what it looks like if we print it out. Now let's run a for loop, starting at 1 and going up to the number of bootstrap samples. Each time, we'll resample 100 observations, which is the number of data points from our data, and we'll do so with replacement. Then, we'll run our numerical optimization algorithm using the sample data, and we'll store the maximum likelihood estimates for that sample to the ith row of our MLE_samples matrix. Here's what the matrix looks like after we've run the for loop. Then, we can obtain the standard error from mu by taking the standard deviation of the first column and the standard error for sigma by taking the standard deviation for the second column. So you're probably thinking, wow, that's a lot of code to obtain standard errors when we could just do it in 2 lines with Fisher information. Why would we ever do that? Well, bootstrapping will come in handy later when we calculate confidence intervals, but another reason you might want to do this is if you want to obtain standard errors for the model predictions. Let's say, for example, that we've run a linear regression using maximum likelihood, and we obtain standard errors for the intercept alpha and the slope beta using either Fisher information or bootstrapping. Well, that's great, and we can plug these values of alpha and beta back into our regression equation to obtain predicted values of y for any given value of x. But what if we want the standard error of our predicted y values for any given value of x? The standard deviation of the mean of what's called the conditional mean of y. The standard deviation of mean of y, which we'll call the conditional mean of y. Well, one thing we can do is bootstrap our maximum likelihood estimates of alpha and beta, and for each of those estimates, obtain a fitted regression line. Each of these, darn, bummer. There we go. See, now it's applying all those lines. Each of these regression lines is going to differ a little from the overall maximum likelihood estimate. To obtain standard errors for y and any given value of x, we just take the standard deviation of the fitted y values at every x value that we've evaluated this for. Now, it turns out this isn't necessary for linear regression because we can use some relatively simple math to obtain the standard error of y given x. But for more complex models, this can be difficult or impossible to compute analytically, so bootstrapping is going to be our friend. Now let's say we've obtained the maximum likelihood estimate and its standard error, and let's say that those happen to be 0 and 1 respectively. Now let's additionally assume that the maximum likelihood estimate is normally distributed, so its distribution is standard normal. Pictured here then is the distribution of our maximum likelihood estimate. What if we want a window which contains 80% of the probability of this estimate's distribution? We call this an 80% confidence interval. Note that this isn't an interval, this is not an interval, which has an 80% chance of having the true value of our parameter in it. This is a window which contains 80% of the probability distribution of our maximum likelihood estimate, and it either does or does not contain the true value. A little confusing, I know, and I'm going to tell you not to confuse these two things, but I literally do it all the time. Anyway, let's bring this fellow back into this picture. This is, as you hopefully recall, the cumulative probability density function for the normal distribution. Recall that it starts at 0, and as we cover more and more of the possible values of our random variable, it climbs to 1. So to find a symmetric 80% confidence interval, that is a confidence interval with 80% of the probability left out of it on each side, or 10% rather, of the probability left out of it on each side, we need to find the places where our cumulative distribution function equals 0.1 and where it equals 0.9. So let's draw a couple horizontal lines through the cumulative distribution function, and let's see where each of those lines intersects it. In the case of the maximum likelihood estimate, in the case of a maximum likelihood estimate that happens to have a standard normal distribution, those values are about 1.3, negative 1.3, and 1.3, which gives us our 80% confidence interval. Earlier on in the lecture, I mentioned something called the inverse cumulative distribution function. This is that function. We give it a quantile, like 0.1 or 0.9, and it tells us where in our distribution that quantile lies. So here's one way that we'll often see this written. Let's say that we want an alpha equals 0.05 confidence interval. which means that we want an interval containing 95% of the probability of the maximum likelihood estimates distribution. If the maximum likelihood estimate is normally distributed with mean mu and standard error sigma, then the confidence interval is the value of the inverse cumulative distribution function, which we'll denote with phi up to the -1 here. The value of the inverse cumulative distribution function for a normal distribution with the mean at the maximum likelihood estimate and standard deviation or standard error sigma, which is our standard error of our maximum likelihood estimate. We evaluate this at alpha over 2, which in this case is 0.025, and at 1 minus alpha over 2, which in this case is 0.975. Luckily, it's often the case that the maximum likelihood estimate is normally distributed, so we can use this quite often. We can use the standard errors from Fisher information or from bootstrapping to estimate confidence intervals this way. Here's how we do that in R. If we have 100 random samples from a standard normal distribution, and we've obtained a maximum likelihood estimate and a standard error for the mean of this normal distribution, then we can calculate a 1 minus alpha confidence interval with the inverse cumulative distribution function, which for the normal distribution is encoded in the Q-norm function. Take a minute to understand how this code works and look up the documentation for Q-norm if you need. When I ran this code, this is the output of my call to Q-norm look like. It says that 95% of the probability of the distribution of the maximum likelihood estimate of mu lies between -0.22 and 0.08, assuming the maximum likelihood estimate is normally distributed. But what if it's not the case that the maximum likelihood estimate is normally distributed? Well, one way to obtain confidence intervals is directly from the distribution of our bootstrap samples, which is known as the bootstrap distribution, intuitively. Here, I've obtained 1,000 bootstrap samples of the maximum likelihood estimate for mu and sigma using the same 100 data points from a standard normal distribution that I showed in the previous slide. And I've stored them in this matrix MLE_samples. Pictured here is a histogram of the samples, which looks pretty close to normal. If I use the quantile function to take the 0.025 and the 0.975 quantiles from this bootstrap distribution, it produces almost exactly the same numbers. So how do we know whether it's safe to assume the maximum likelihood estimate is normally distributed or not? One way is from the shape of the likelihood profiles we introduced earlier. If the likelihood profile is symmetric in shape around the maximum likelihood estimate, then a normal approximation is usually a good choice. If it's not symmetric around the maximum likelihood estimate, then the distribution of the maximum likelihood estimate likely isn't symmetric either, which means it's not normal. In that case, we can compute confidence intervals either from the bootstrap, using the bootstrap, or directly from likelihood profiles. We can also tell whether or not the distribution of the maximum likelihood estimate is symmetric using the bootstrap distribution itself. If this distribution is highly skewed, it's probably the case that it's not normal. But once we have these bootstrap distributions, we can use the quantile function to obtain a confidence interval whether or not the maximum likelihood estimate is normally distributed. The latter method that I mentioned using likelihood profiles, we won't go over in class, but I just thought I should mention it. So to wrap things up, here's what we learned in this lecture. If we find ourselves in the position of having a deterministic model that we want to explain some biological phenomena we've observed, and we want to estimate the parameters of that model using maximum likelihood, here's what we do. First, we choose a probability distribution which links our deterministic model to our observed data. This is frequently the hardest part. Next, once we know the form of the model and its probability distribution, it's usually easy to code up a function for the negative log likelihood. Then we want to minimize the negative log likelihood using, in most cases, some numerical optimization algorithm paired with the negative log likelihood function that we've defined. This step, however, can be extremely finicky for complex models, as we'll see this week. Once we've got our maximum likelihood estimates for our model parameters, we can obtain standard errors for the estimates using either the Fisher information or bootstrapping. And finally, we can obtain confidence intervals using the parameters, assuming the parameters are normally distributed, or using the bootstrap distribution or using likelihood profiles. So that's everything for this lecture. There's a lot more to learn. If you're interested in understanding some of the fundamental ideas around probability and likelihood, a good book to check out is Statistical Thinking from Scratch by Doc Edge. If you think you've got the basics down and want to learn more, check out Ecological Models and Data in R by Ben Volker. There's plenty more to cover. For instance, we haven't talked at all about how to check if our data fit the distributions we chose, or what to do if it's clear that our data points aren't independent after accounting for the deterministic form of the model. And I want to mention that there's a bunch of packages that make maximum likelihood estimation are a lot easier than how we've done it here. And there's also a bunch of problem-specific packages, such as the FSA package for fishery stock assessment, that implement maximum likelihood estimation for specific problems. Maximum likelihood estimation, however, is really everywhere. If you've ever ran a linear regression, or a generalized linear model, or a mixed effects model, you've used it. It's only when we have highly custom models, which a lot of the mathematical models we've covered in this class are, that we'll want to implement maximum likelihood estimation by hand. Lastly, if some of the things we covered today didn't make sense to you, I want to reiterate that that's okay. We're not going to be relearning, or we are going to be relearning and reinforcing these concepts all week with lab activities. And with that, see you on Monday.